it's a script that generates a sphere, and when you do your homework, you're gonna generate a torus, so you can write the torus script in a separate file, and run the file here. So you're gonna see a torus, just like if I here do Swiss row, and click the bar to run the section. You see because I didn't clear the saved data, so let me just go to the command window to do clear all, and I don't want to see the command windows. You'll see. Okay, so now I have no saved whatsoever. Let me also do close all. Okay. Alright, so let me do this again. Run this line. You should only print out a figure that is the Swiss row. Yep, we have it. Okay, and I have several parameters set up here, and it's the number of points. So this is determined once you generate your data, and Kn, N, and sigma 2 are the parameters you choose. So Kn is used to choose k nearest neighbors of a reference point, and sigma 2 is just a parameter. You can see this as a diffusion time. You can also see this just as a parameter that determines strength of the connection in graph. Okay, so let's just move forward and see what they are and why we would want to have Kn and sigma 2. Okay, so we're gonna use the kernel function kxy or kxij, defined as e to the exponential distance squared over a parameter epsilon, and here I just call the epsilon sigma 2. No specific reason, just because this is the code I modified from someone's code, so I don't want to be touching too much. Okay, and here you can see, if let's say if xi is my reference point, like now I care about which points are closer to xi, and use that to determine the kernel function k. Okay, so you can see that if xj is very far away from xi, then the distance is very large, but with the minus sign and the exponential function, it's gonna give you a very small number because of exponential decay, right? So we may as well just set that to 0. So then it's numerically easier. It doesn't take as much computation time. Okay, so that is why we have this Kn, and this is your choice, like how many points you wanna have in the k nearest neighborhood, and it is also your choice to choose the sigma 2. Okay, so when you change these numbers, you are gonna end up seeing a different embedding when you later run diffusion map. Okay, so now I have about 2,000 points, so I will have to compute pairwise distances between this 2000 points, and that will give me what the diffusion matrix L. And here in this case, we're gonna look at the situation where alpha equals 0. So when alpha equals 0, the denominator here equals 1. So this line is redundant. We don't care about it. Okay? And we have a diagonal matrix defined this way. So it's a diagonal matrix, and each entry dii is defined as the sum of Lij over j. So it's like summing over columns. Yeah. Okay. Then you have because alpha equals 0 here. So here you just the inverse. What you have is just the inverse L, and this is your graph Laplacian. Okay, and you're gonna use the graph Laplacian to find eigenfunctions and eigenvalues. And by eigenfunctions, I actually mean eigenvectors, because now it's discrete. Okay, so here the dt gives you pairwise distance among all those 48 points. But like we said, we don't want to have all of them, because then it's like too much computation. We don't want it. So we only say, okay, let me look at for each simple point, I only want to look at its k nearest neighbors. So that is how I have my new dt. Okay, so my original dt, you can see that let me just run this line here. You can see dt is a matrix of size 248 by 2048 by 2048. Okay, so because I have 2048 points on my surface, but after oops, I forgot to run this section, so it doesn't recognize what kn is. Okay, so now let me then sorting the distances, only pick the smaller ones. So now you can see my new dt only has its size is only 63 by 2048. So that means for each point, for each simple point, only consider its nearby points, and I only look at those 63 points. Okay, and now I have a matrix defined as exponential times minus distance squared over sigma 2. Okay, so this, if you look at the formula, you can see that that is the diffusion matrix in our formula. All right, then I wanna build a weight matrix. So this step is just to make sure that I have a symmetric space. I don't symmetric matrix. Okay, so this is just the so this step here is just kind of like making sure we have a symmetric matrix. Okay, and the sparse command and rep map, it's just like a way to save energy, so not save memory. Okay, so I mean, the most naive way is you're gonna just deal with a huge matrix of size 2048 by 2048, but that will take up a lot of space in your computer, memory space in your computer. So this is just a different way to write the weight matrix. Okay, and wanna make sure there's no like numerical issues. Make sure this is symmetric, and we can later do normalize the graph Laplacian. So that is this part. Okay, so that's this part, and I will talk about this later. So this will give us the eigenvalues and the eigenfactors, i.e. eigenfunctions. Okay, so Ix is the command that helps you to find top eigenvectors. Here I put 10 because I said, okay, let me find me the first 10 eigenvectors. So it returns eigenvectors with eigenvalues. Okay, so let's see if I run this section, we'll see. Where's V? Yeah, you see, V is a matrix of size 2048 times 10. So this, let's click this. Okay, so this is the first eigenvector on the sphere, and this is the second eigenvector on the sphere, and each value is the function value. You can think this is a function value at that sample point. So because of 2048 points, so that's why we have 2048 values. Okay, then of course we say, okay, let me use these eigenvectors to do diffusion map, to map the manifold into another Euclidean space. Okay, so here I choose 3 vectors, and as we learned, the first eigenvector is pretty much the constant, and you can see that it's pretty consistent. 0.0213, 0.0211, 0.0211. So it's like so this little discrepancy is basically from numerical issues, but you can see it's pretty much like a constant. Okay. So we go back, and this is what you see. All right, so let me show you if I wanna do a 2-dimensional plot. So I'm gonna do scalar, and now I can only have 2 coordinate functions. So let me do this. Okay, so here, hold on a second. Okay, so you can see that it gives me a two-dimensional image. Okay, or image in a 2-dimensional space. All right, so I don't want this. Close it up. Put it back to a 3-dimensional space. Okay, so this is how you can play with that. All right, and the next one is where we let alpha equal 1. So what this means is now the formula down here is not redundant, the formula down here is not redundant. So once we have our initial temporary weight matrix, which is the initial L, then we have to follow this line here, this formula here. So make sure we have a symmetric weight matrix. And now I create a diagonal matrix. Then you see I call this diagonal matrix new, is it ID or LD? Oh, it's a LD. Okay, so new LD, and I'm gonna do new LD times W times new LD. And remember, this is W, or this W is the Lij in the formula. So this line here, 21, is equivalent to LO per parenthesis 1 in the formula above. Alright, and then we go ahead, compute eigenvalues and eigenvectors. So I just call this new V and new D. I don't think this was like a good name, but I don't have a better name either, so let's just use this. Okay, and now I choose the first 10 eigenvectors. So because in my visualization I only print out 3 vectors, or like I only use the second, third, and fourth vectors, so I actually don't have to go up to 10. I can just go up to 4 or 5. But when we're not doing visualization, and when we're like just say like, okay, suppose I want to put this manifold in, let's say 10 dimensional space, and I want to look at the diffusion distance for the embedded surface, then it makes sense to have more eigenvectors, and you actually need more eigenvectors because you're using more eigenvectors or eigenfunctions to compute the diffusion distance, right? So it's just when it's in high dimensional space, we cannot print out, we cannot see it, but we can still compute the numbers. All right, so here's this number 10. Okay, you can change this. All right, so now you can see my why is it blinking? I feel like my computer is going crazy. Okay, so anyways, so I have the original data on the left, and this is what's going on? Okay, all right. So now you see that I have my original data on the left and the printed out data on the right. Okay, so that's it. And you can the sphere comes from before. So again, this is coming from, I didn't erase my previous data. So so you can see that I have something weird coming up. So the best way to do this is just do clear all variables, close all. If I have open windows for figures, I want to get rid of CLC to clear my command window. Okay. Alright, 1 second. Let's run the script again from the top. Okay, I see. Alright, yeah, so I called for sphere. Right. And so I should have an embedding for the sphere. Right, okay, so this is what I have. Okay, so now you can play with this.